So welcome back to another video. So this time we have a problem of to evaluate when the limit as n approaches infinity of 2 cubed minus 1 divided by 2 cubed plus 1 multiplied by 3 cubed minus 1 divided by 3 cubed plus 1, and then multiply so on and so forth to n cubed minus 1 divided by n cubed plus 1. So we have a product here, so with that, let's actually get started. So let P equals this limit here. So pretty much I'm just rewriting this, our given. So this is 2 cubed minus 1, 2 cubed plus 1, multiplied by 3 cubed plus, or minus 1 divided by 3 cubed plus 1, multiply so forth to n cubed minus 1 divided by n cubed plus 1. Okay, and just like I said, this is actually a product series, so this is from our index can start at r is equal to 2, like our starting, and then all the way up to infinity of r cubed minus 1 divided by r cubed plus 1. Okay. Now, let's actually take the natural log of both sides. So the natural log of P equal to the natural log of the product at r is equal to 2 to infinity of r cubed minus 1, r cubed plus 1. Okay. And then notice that that's actually the same thing as the summation from r equals 2 to infinity of the natural log of r cubed minus 1 divided by r cubed plus 1. And why is that? Because if I take the natural log of the product series, this equals to the summation, mainly because of by continuity of the natural log. So this actually converges to ln of p, where it's also equal to it can also be rewritten as the summation of the natural log of our rational function in particular. Okay, so far so good. So now that we have the natural log of r cubed minus 1 divided by r cubed plus 1, we can actually use the natural log rules so that we can actually write two summations, and this is under division in the natural log, so we have to use subtraction. Again, we're writing this as two series of natural logs. So this is ln of r cubed minus 1, and then subtract infinity r is equal to 2 of the natural log of r cubed plus 1. All right, and then let's actually note something here. So r cubed minus 1 can be factored out into products of polynomials, specifically r minus 1, and then multiply by r squared plus r plus 1, and then r cubed plus 1, it can be rewritten as r plus 1, then multiply by r squared minus r plus 1. And I could actually factor out the r from both the top and bottom, so we get r minus 1, then r times r plus 1 plus 1, and then same thing like before. This is a plus right here, and this is r, then r minus 1 and plus 1. Okay, nice. So far so good. So now we can actually substitute our factored polynomial, cubic polynomial. So that means we're actually still taking natural logs of r minus 1 multiplied by r times r plus 1 plus 1. Same thing with the other one as well. We can still apply natural log rules. So this time we're actually going to get 4 different summations. So with that, since r plus 1 replace here, you remember you need to distribute the negative. And what I'm going to do is it's distributing the negative and it's still commuted under addition. So I'm actually going to write these two terms, the natural log of these two terms come first as our first two terms, and then the other one here. So this means we have summation r equals 2 to infinity of natural log of r minus 1, then plus, or this is actually supposed, that's actually minus right here. That's a minus, and then r equals 2, natural log of r plus 1, and then plus the summation r equals 2 of natural log of r times r plus 1, and then subtract r equals 2 natural log of r minus 1 plus 1. Okay, so now the next step is going to be interesting. We're actually going to, specifically these two terms here, we're going to change their indexes such that the natural log of r minus 1 matches with this natural log here, and then the natural log of the inside is going to match with this. But they'll end up with different starting indexes. So let's start with the first term here. So again, another note, the summation of r equals 2 of ln of r minus 1. This is actually the same thing as our index starts at 1, but that'll simply mean it's just ln of r. But this also can be, this is actually equivalent when the index starts at 2 of ln of r. Why is that? Is because if we were to evaluate r is equal to 1 of ln of r, that's actually 0. Then you start with the next term, which is 2, so that will start with ln of 2, then plus ln of 3, and so on, which is exactly the same thing as what we written right here. So this, these two equal to each other, and with that I can actually rewrite this as, so again, start our index as r is equal to 1 of the natural log of r plus 1. Okay, and now let's actually change our index from over here. So the summation of r equals 2 of ln of r times r minus 1 plus 1 is equal to, now we're going to start our index as r is equal to 1 to infinity of ln of, so let's see, 2, so 2 minus 1 is 2, so 3. So that means this is ln of r, and then r plus 1 plus 1. So yeah, if I plug 1 here, 1 here. Okay, yep. All right, so now we have that. Let's actually do our, substitute our pieces. So this way we have the, let's see, that means, yep. So now we have r is equal to 1 of right here, so ln of r plus 1, then plus the summation, or this is actually, let's see, this is a minus, as a matter of fact. So this is minus summation r is equal to 2 of ln of r plus 1. I'm actually going to move to the next line. I think if you can't tell the camera, there's like lighting blocking over this side. So if I were to write over here, I think it's like impossible for you guys to see like what I've written. So that means plus summation of r is equal to 2 of ln of r plus 1, and then plus 1, and then subtract the summation r is equal to 1 to infinity of ln of r plus 1 plus 1. You guys can see that, right? Yeah, you can sort of see it. They're basically the same thing, except this, our index starts at 1, and then our index starts at 2 over here. So it'll be fine. Okay, so now that we have that, now what we're gonna do now is we're going to evaluate these sums. So far we have that ln of p is equal to our 4 series, the summation of our 4 series. So what we want to notice is that if you think about this, r is equal to 1 and then r is equal to 2 when they have the same natural log of r plus 1. R is equal to 1 is going to have a bigger series than the r is equal to 2. So that means if I were to subtract, so that means we're left with So if you want to evaluate each series out, let's say, so let's notice that our starting r equals to 1, so ln of r plus 1, so ln of 2 is here, and then subtract ln of 2 plus 1 is 3, that's the starting. Really, when you think about it this way, you could think of it as more of like a telescoping series. So these are series where, like, when you expand them out, you're going to have terms that are going to cancel each other where equal to 0. So this means we're going to have like some left over for focusing on these two. So really, when r is equal to 1, that means this is ln of 2, then it's 2, so that means ln of 2 plus ln of 3 plus ln of 4 and so on for here. But then we have subtraction of ln of 3 minus ln of 4, ln of 5, and then so on. But since it's subtraction, they actually cancel out. But the only thing you're really left to evaluate is ln of r plus 1 when r is equal to 1 specifically. So when r is equal to 1 of ln of r, that's actually just ln of 2. So let me actually write it like this. So let's just focus on these two summations. So to reiterate, r is equal to 1 ln of r plus 1, right? And then subtract r is equal to 2 of ln of r plus 1. Again, the concept of telescoping series, the terms cancel out. Really, we only have to evaluate when r is equal to 1 of ln of r plus 1, when it's actually just equal to ln of 2. Okay? Now, the same thing can apply for here. So, let me actually write out the same format like before. So sigma r is equal to 2 ln of r, and then r plus 1, then minus ln of r plus 1 plus 1. Okay, so as I said before, usually when when r is equal to 1, it's usually the smaller indexes compared to here, it's going to be the bigger sum. So if I were to plug r is equal to 2 for here, so we start out with ln of 2 times 3, 6, yeah, and then plus 1, 7. So, and then 3 and so on. But we start with r is equal to 1, so ln of r ln of 1 times 1 times 2 is 2, then plus 1 is 3. And again, telescoping series, the terms are going to cancel out. So what we really need to evaluate is when ln of r times r plus 1 as r is equal to 1. So when you evaluate that, you're going to get ln of 3. All right. So now that we have that, or this is a minus specifically because there's a negative right here. So now really we have ln of p is equal to ln of 2 minus ln of 3. Now we can actually use natural logs again, so ln of p really is equal to ln of 2 divided by 3, and then we can take the e, our base e, to both sides, so we get ln of p equals e to the ln of 2, oops, that's a 2 over 3, when really e to the natural log cancel out, so therefore p is equal to 2 over 3. All right, so let me just write the final conclusion. Just write this in black. So 3 dots, shape in a triangle, that signifies therefore our limit as n approaches infinity of 2/3 minus 1, 2/3 plus 1 multiplied by 3/3 minus 1 divided by 3/3 plus 1 multiply, series continues, to n cubed minus 1 divided by n cubed plus 1. It is equal to 2 over 3. And I'll just circle this in pink again, or I'll box it. Actually, I think a box looks nice, like so. All right, and we're done. That's a pretty awesome series.